Well, I would like to thank the organizers for inviting me. It's always a pleasure to be in Lumini. Okay, so I'm actually going to start by writing down the theorem, and then I'll introduce some of the background. So this is joint work for a very, very long project, just like the long intervals I'm going to talk about. That started, which week? It was the second week of May 2020. So it was a pandemic project. And the people involved were Hayut, James Cummings, I guess, sorry, alphabetical. Yeah. Cummings, Hayut, Menahem, Itai, myself, and Spencer. Okay. So this was one of those AIM square groups. And we were working on the tree property, and we're trying to work towards that old project in set theory to get the tree property everywhere. Well, we didn't get it quite everywhere, but we got it for a very long, long time. So from large cardinals, there is a forcing construction. So forcing extension where the tree property holds at every regular cardinal in the interval Aleph 2, Aleph omega squared plus 3. Okay. Okay, so now let me go back to the beginning and tell a little bit what is the tree property, what motivated this theorem, and what were some of the challenges along the way. And then, time permitting, I will talk a little bit about some open problems and what is the next step in this project. So the tree property is an analog, an uncountable analog of Koenig's infinity lemma. So remember, Koenig's infinity lemma is the statement that every infinite, finitely branching tree has an infinite branch. So each infinite, finitely branching tree has an infinite branch. Okay, so this can be thought of as the tree property at omega. The tree property at kappa generalizes this statement for trees of height kappa. So in other words, if T is a tree, height kappa, levels of size less than kappa. Okay, let me say less than kappa levels, less than kappa sized levels. Then it has a cofinal branch. So there is let's see. And So by Cummings lemma, the tree property at omega holds. So the next question was, okay, what about the tree property at omega 1? Namely, if we have uncountable tree with branches of countable levels, do we always have an uncountable branch? And the answer to that is not. So the tree property fails at omega 1. So in other words, there is something called an arrangement tree. Okay, so this is the story for omega 1. What about the second uncountable cardinal omega 2? And well, if one wants to get a counterexample, the natural thing to do is try to take the arrangement construction and see if you can do it one cardinal up. And morally speaking, you can, as long as you have the right cardinal arithmetic. So if you have CH, then the tree property at omega 2 fails, morally speaking, by a similar type argument. And okay, so what about positive results? Let me say. Getting the tree property, well, it turns out that if you have large cardinals, you can get the tree property. Actually, the tree property is a very key instance of something referred to as the so-called compactness phenomenon. Namely, what is compactness? So compactness means given an object of some size kappa, if something is true for every strictly smaller substructure, it's true for that object. Now, why is the tree property such an instance? Well, you have a tree, and know that, of course, at every level in the tree, you can find this so-called uncountable branch restricted to that level. And what the tree property says that if this happens, you can actually find it for all an unbounded branch through the whole tree. And so let me do a little proof by picture, which somehow, although it's very simple, really contains the spirit of how we prove the existence that the tree property holds in almost any situation. And I'm going to use a measurable here. So we have the following fact. If kappa is a measurable, then the tree property holds at kappa. You don't actually need a measurable. The tree property is modulo inaccessible, equivalent to a weakly compact, but I'm going to do it with a measurable. So what is the proof? Well, okay, so we have our tree T of size kappa, and kappa is measurable, so one does the only thing really you can do, which is hit it with your elementary embedding J, and then look at J of T. Now, J of T is a tree of size J of kappa, so what does one do? You take any node U on the kappath level of J of T. Now, trace its predecessors, that's a branch up to you, and then you can pull it back to get a branch. Oh, I can even use colored. To get back a branch through the tree, original tree. So where did we use the fact that the sizes are of less, the sizes of the levels are of less than kappa? Well, it's in the pulling back. You need to use that they're below the critical point. So somehow one can actually prove that the subtree here is exactly the image, pointwise image of the tree here. Okay. So this is the picture, and although this is a very simple picture, as we'll see throughout the talk, is somehow at the heart of how one proves the tree property. Okay. So then, at L of 2, what is the idea is to take a large cardinal and turn it into L of 2, right? Maybe measurable, or all you need is actually a weakly compact. Now, collapse wouldn't work. If you take, let's say, kappa is a large cardinal, well, you actually just need weakly compact. So know that this doesn't work. And the reason it doesn't work is because the Levy collapse will force CH. And CH, as we didn't see, but as we know, not forces, but implies that the tree property would fail at omega 2. There is a counterexample. So instead, what does one do? Well, this is the Mitchell's famous result. So Mitchell's forcing. And I'm not going to define it, but I will draw a picture. So we have some large cardinal, so weakly compact kappa. Let's see, this is omega 1. Well, there are two tasks this forcing has to do. One is to blow up the power set of omega to kappa. To make. And for that, it uses Cohen forcing as part of its definition. And two, at the same time, collapse cardinals between omega 1 and kappa. No. And make, therefore, kappa becomes L of 2. Okay? So, and then, so we do all this, and then we go back to this picture and hope it somehow works. Of course, kappa is no longer a large cardinal in the generic extension, but it was formerly a large cardinal. So the proof of the tree property relies on taking an elementary embedding such as this from the ground model, where kappa was a large cardinal, lift it to the elementary extension, so lift it to the generic extension, get a branch defined just like in the picture, and then prove that the branch is in the right model. So what do I mean by that? Okay, so you have, if you start with V, you have your kappa and your elementary embedding, taking kappa to J of kappa. So the first step is lift J to the generic extension. Okay. And then, again, you do this picture with the trees. You get a branch. But now this branch is no longer in VG, so it's not like over there, because the branch is used, the definition of the branch uses J, your lifted elementary embedding. So this branch is in the outer model where this lifting happens. So this branch is in some VG H, where you can think of H is, roughly speaking, a generic for J of the Mitchell modulo the Mitchell, right? So if the Mitchell forcing makes, kappa to be L of 2, it's in VG. In M star, know that kappa will be collapsed now, right? So here, kappa is collapsed to omega 1 because J of the Mitchell will make J of kappa L of 2. So this is a non-trivial extension. And then the second step is to pull back. So use a branch lemma. So-called branch lemma to pull back the branch to VG, namely to show that this H, the extra forcing we had to do in order to leave the elementary embedding, could not have added a new branch through a kappa tree. So the talking point, to summarize like both of these parts of the board, is to get the tree property, you lift an elementary embedding and then use a branch lemma to pull back the branch. As we'll see, this is somehow like the central block in every little part of the forcing construction we're going to be doing in order to prove the tree property at successors of regulars. Okay. All right, so I'm going to lift those boards up. Oh, it doesn't do simultaneously. Okay, so around the times I didn't write when this happened, this forcing, Mitchell's forcing was in like the 70s, I think 72. Let me do the historical survey, a little bit of results on 72. Mitchell got the tree property at L of 2. And then there was this question asked, maybe a little bit later, by Magidor and others. Well, can we get the tree property at each regular cardinal above L of 1? Okay. It only makes sense to talk about regular cardinals because, at a singular cardinal, having hide that cardinal actually collapses to its cofinality, so it's very easy to get a counterexample to the tree property. Okay. So what was at first the progress was steady, but slow but steady. So back in So in 72, there was the Mitchell result. Then in the Reagan administration, Abraham showed that you can get the tree property from large cardinals for L of 2 and L of 3 simultaneously. Now, while Mitchell's forcing uses only a weakly compact, this construction uses significantly more large cardinals. So it uses a weakly compact and above a super compact. All right, so what about for all the LFN? So during the Clinton administration, Cummings Foreman showed that one can get the tree property at LFN for all n greater than 1. Okay. And what about adding L of omega plus 1? So this was done by Itai, I guess. Well, let's make it Obama administration, although he really proved it in 2008. So from large cardinals, he got the tree property at L of n for all n greater than 1. And the tree property at L of omega plus 1. Now, what is the big challenge in adding L of omega plus 2 here? By the way, in both of these results, L of omega is strong limit. Here, omega is strong limit. Okay. Well, in order to get the tree property at alpha omega plus 2 with alpha omega strong limit, one will have to violate SCH at alpha omega. And this goes back to, I mean, morally speaking, it's similar to the argument that CH implies the tree property at alpha 2. So, more generally, due to Specker, I'm going to write the corollary of the actual theorem, that if kappa is singular strong limit, and you have the tree property at kappa double plus, then you need SCH to fail at kappa. And so far it's open whether, so in all of this construction, SCH at alpha omega holds. Okay, so what happens in this situation when kappa is singular strong limit and you want to get the tree property at kappa double plus? So you have to violate this SCH in a way where, if you also want to preserve the tree property or have the tree property at kappa plus, in a way which doesn't add square. So what is the, like, a big challenge here? Oh, the usual challenge. Most forcings which violate SCH at kappa forcing failure of SCH at kappa adds weak square at kappa. So for example, if you just do vanilla precree, you add square kappa omega even. And there is a theorem that weak square at kappa implies that there is an Arrangian tree at kappa double plus. So if you want to get the tree property at kappa plus and kappa double plus, you have to first figure out a way to force SCH to fail so that this doesn't happen. Yeah. Sorry? Yeah, but we want to get it at both, right? Yes, so this is correct. So somehow we don't want to just get the tree property at kappa double plus. We want to get it at both. Yeah. Okay. And actually, let me do, well, juxtapose kappa plus and kappa double plus, I guess, on this board. So just a little bit of the history. So here, if kappa, so in the case of kappa singular strong limit, and we want to get both P at kappa and kappa double plus. So what are some results that led up to this project? In the James and Matt paper, they also showed that by interleaving a precree forcing in Mitchell, you can get the tree property at kappa plus. But in this construction, weak square at kappa holds. So what I mean when I write this, so the theorem is from large cardinals, there is a forcing extension where the tree property holds at kappa double plus, and kappa is singular strong limit. And then Itai showed, building on a work of Gittik-Sharon, that one can get failure of SCH at kappa. Oh, first, before him, oh no. Let me do another result. So the first result of getting the tree property at kappa plus was Magidor-Shella, who showed that if kappa is the limit of supercompacts, then the tree property holds at kappa plus. Now, of course, in this model, SCH holds kappa, and then Itai using a forcing, well, a modification of a forcing defined by Gittic and Sharon, show that so we can get the tree property at kappa plus and failure of SCH at kappa. Okay. And then the next kind of task was, well, bring this down to smaller cardinals. And we haven't been able to bring it down to aleph omega, but after a few attempts, Spencer and myself got it at aleph omega squared plus 1 and plus 2. With aleph omega squared strong limit. So somehow on this board is the situation that was the case when we started working on our theorem about successors, the first and the second successors of singular strong limit cardinals. And this motivated our strategy of creating a forcing extension where, I mean, we still don't know how to add aleph omega plus 2 when aleph omega is strong limit. But what we did is a forcing construction where aleph omega squared is the first strong limit. Then you can, get over this hurdle posed by Specker's theorem. So in our construction, by our I mean the main theorem. In the final model, aleph omega squared is the first strong limit cardinal. Okay, so let me summarize some of the building blocks before I get into just a picture of what our forcing was. Well, so to sum up so far, so I want to divide it into two categories. Well, to get the tree property at kappa plus, where kappa is a regular, I mean, it's basically that picture in this board. You have to lift, let me write it like that, lift and pull back. So you take an elementary embedding from some ground model where your kappa plus used to be a large cardinal. You lift this elementary embedding to the correct model where kappa is now a successor. You define the branch, and then the branch is in an outer model. So you need, and we have a whole basically chapter of branch lemmas devoted to how you pull back a branch. Yeah. Now, to get, and also we need, so lift and pull, and we need like a Mitchell-like forcing. So we also need many failures of GCH. So in this construction, so here there's just a failure of CH, but this construction can be generalized if you have kappa n plus 1, kappa n plus 2. So what do? You make 2 to the kappa n equal kappa n plus 2, and collapse cardinals between kappa n plus 1 and kappa n plus 2. So this is kind of like the abstract module from Mitchell's forcing. So this can be generalized to any triple of cardinals. Okay. So we need many, many such blocks of forcings in order to get the tree property at successive successors of regular. So for example, going back to the James and Matt's model of obtaining the tree property at L of n, for every n, what they did is like this, like an omega, you can think of it as an omega iteration of Mitchell type forcings. Okay. But now to combine this with tree property at the double successor of a singular, you need failures of SCH. So, and of course, for all of this to happen, you need many large cardinals to start with. Okay. So somehow, any answer to positive answer to this question, getting the tree property everywhere or even at long intervals of cardinal, will need to follow like those 4 bullet points. Yeah. Okay. So let me draw a picture. Next. I don't know, which board should I use? Or maybe this one. So I'm going to draw a picture of the cardinals. Okay, so we have, okay, so suppose we have, okay, so we have our kappa. So this is the cardinal destined to become L of omega squared. So let me anchor everything around this kappa. Now, okay, so what is like a warm-up? What was the forcing to get some of these results? Well, I said that it was a variation of Gittig-Sharon. So this is kind of a warm-up picture. Pick is take kappa to be the sub of supercompact cardinals. And why is that the natural place to start? Well, this goes back to the Magidor-Schauer result, that in order to get the tree property of a successor of a singular, you need that singular to be the limit of supercompact cardinals. So we have this, okay, no, sorry. Kappa is actually going to be the first one of these guys. So warm-up pick, let kappa and n less than omega be an increasing sequence of supercompact cardinals, and let kappa be kappa 0. Okay, so kappa is the first. And then you have these kappa n's. So now, as I said, kappa is destined to become L of omega squared. So we force with a Prickry type forcing, so diagonal Prickry type forcing, using measures on P kappa n. And if you don't know what that means, well, I'm going to tell you. So the original vanilla Prickry forcing used a measure on a measurable cardinal kappa to force a Prickry sequence through kappa. Now, supercompact Prickry forcing uses a supercompact measure on P kappa n in order to force Prickry sequences singularizing an interval of cardinal. So it will singularize every regular between kappa and kappa n inclusive. And we do this diagonally, so we do this for every n. Like this forcing, if we take, suppose the limit of these cardinals is kappa omega, this forcing will collapse kappa omega to kappa, and it will singularize every regular cardinal in this interval between kappa and kappa omega. So the new successor of kappa will be the old successor of kappa omega. So kappa omega plus, we call it mu, now is destined to become L of omega squared plus 1. Okay. All right, so with a little bit of blood, sweat, and tears, this construction can be adapted so that you interleave collapses below kappa, which makes kappa to become aleph omega squared, and mu become aleph omega squared plus 1, and you prove that the tree property at mu still holds after you've done all those things. Know that in the beginning, before you start forcing, since mu is the successor of a singular, by Magidor and Shell's theorem, the tree property holds there. So the point of the proof is to show that the tree property still holds after you've done all this forcing over the ground model. Okay. Okay, so this is how one can get it for the successor of a singular. But now what happens below kappa? So let me pinpoint two prickly points. Let me call them taus of n plus 1, tau n. So this is the prickly sequence added to kappa. Now, let me do 2, tau n plus 2. So the next question is how to get the tree property at the, at the tau n's. Well, at the tau n's and their successors, right? The tau n's and any cardinals that are left between them, and preserved cardinals. Okay. So, well, the idea is to go back and do something like this, some sort of a mutual type forcing. But now there is, right away, there is a dilemma. You can either do it in some preparation forcing before you do the prickly, or you can interleave it with the prickly. And I remember when we were working on this, we kept first doing one, then the other, and somehow it was like, like that cartoon with the mushrooms, like you take care of one and then another one pops up. And in the end, what helped us, what made the construction work, is for some of these cardinals below kappa to do the preparation in advance to get the tree property at the end, and for others to interleave it within the prickly forcing. So let me try to write some of this. Okay. Okay, so, overview. So now I'm going to talk about overview of our construction. Forcing. And there were many parts in it, but I'm going to anchor it around this cardinal kappa and the prickly forcing that adds sequences through kappa, because if you haven't seen prickly type forcing, just think to yourself, back to the vanilla prickly forcing. And we're just doing like an upgraded version of that. So instead of one prickly sequence, we're adding many prickly sequences in this interval. Okay. Mm-hmm. So let P be the diagonal prickly forcing. Okay. Defined in, okay, so in some, model, let me call it V prime, which is obtained from our original model V after some preparation. So, and this is like a laver type preparation several times over. And to get the tree property below kappa, Okay? So how many cardinals are below kappa? Well, Aleph omega squared, right? So I should say defined in V, P's with interleaved collapses. With some interleaved collapses. Not Levy collapse, but it's a Mitchell type collapse in order to make kappa Aleph omega squared. And now to get the tree property below kappa so we divide the cardinals in two groups. And we call them the A block and the B block. And the division is that for one of them, we prepare the model to force the tree property to hold in advance before the pre-cre. So the B block, we get the tree property in V prime before we force over the pre-cre. And in the A block, we get the tree property via Mitchell type forcing in, let me say, in the P forcing, so in the pre-cre forcing. Okay. So with that in mind, I'm going to draw another picture. Let me draw it here. Do I have until 10 or 9:50? 9:50. Okay.
Well, maybe coming into practice a bit.
Okay. Okay. All right, so again, I'm going to anchor them over kappa. So instead of just taking one set of supercompact cardinals above kappa, we're going to take two. So here, so this is the A block. So lambda ANs, which are all supercompact above kappa, and this is the B block, lambda BNs, which are also supercompact cardinals. Okay? And when we do the pre-cre, so we're going to use measures UN, so P uses measures UN on P kappa lambda BNs. So in the end, so kappa is destined to become Aleph omega squared. Aleph omega squared plus 1 is here. It's above all the blocks. So all the blocks, both the A block and the B block, get collapsed by the pre-cre sequences with these measures. But the thing is, when one looks at cardinals below kappa, any two pre-cre points below kappa have their own reflections of the A block and the B block. So below kappa, so if you have if tau n is a pre-cre point, we have here mini A block and B block associated with every such pre-cre point. And this is like a natural phenomenon when one does pre-cre forcing. Again, let me go back to a very simple case of vanilla pre-cre. Suppose you have kappa, and it happens to be that 2 to the kappa is kappa double plus. When you force just a vanilla pre-cre sequence, then if the prickly points are tau n and less than kappa, for each n, 2 to the tau n will be tau n double plus. So the prickly points reflect the situation, below kappa reflect the situation at kappa. And since we take, and we need a lot of large cardinals here, our situation is that we have kappa and we have 2 blocks of omega many supercompact cardinals above it. This, in some way, is reflected at every prickly point below kappa. So then the next prickly point will be somewhere over here. Okay. And the prickly forcing P, the collapses that it has in order to make, it has to collapse many of those cardinals in order to make kappa alpha omega squared. It does so in a Mitchell type forcing. Maybe you can even kind of see it from what I erased here. But so for the A block cardinals, we force the tree property with, well, it's really like, let me call it an omega iteration, although iteration is not the right word, of Mitchell type forcings, of Mitchells at, so in the same spirit as the Cummings Forman and its ice construction, in the spirit of and this is like the module that we interleaved within the prickly forcing. Now, the B block, here we get the tree property in advance. And the tree property N and collapsing in between. So what does that mean? Well, this is an omega, so let me, this B block, reflects this B block. And in either case, so there is the same picture, we have omega many cardinals, lambda bn plus 1, etc. And we do a Mitchell type, omega Mitchell type iteration in advance to make these, to make the successors of each other, so collapsing cardinals in between, and blow up the power set so that for all n, lambda bn has power set lambda b n plus 2. So in advance, i.e. with a Mitchell type iteration over the original lambda b block. Okay. So this is roughly kind of the picture.
The 2 blocks are interleaving each other?
No, they're not. They are, so this is omega many supercompact cardinals, and then above them is omega many supercompact cardinals. So these are each of these represent.
So you have order type omega plus omega of supercompacts above kappa and below what becomes aleph omega squared plus 1.
We actually start with even more than omega plus omega, but after some pigeonhole choosing, we choose 2 omega blocks of supercompact cardinals above kappa, so that a lot of their properties reflect below kappa. So here they'll be, because these are supercompact cardinals, for example, the tree property would hold the successor here. We want this to reflect for the tree property of the successor of the little b block below kappa associated with the prickly point. Okay, and there's one component of this picture, this construction that I haven't mentioned yet. It's somehow, in a way, so this is about what we do with the successor of singulars below kappa. And for reasons similar to what Hans was talking about in his talk, we have to choose omega 1 very carefully. So let me talk a little bit about choosing, choosing omega 1. So now I'm going to draw my final picture, and we did start a little bit late, so I'll take. Okay. So tree property at successors of singulars below kappa. Okay, well, so if you have here, kappa is here, and here you have some successor of a singular. Let's call it lambda omega plus 1, as in successor of a singular. Well, we arrange everything so that this lambda omega plus 1 is a reflection of lambda, either the supremum plus of the A block or the supremum plus of the B block. And so there is this theorem that given an omega many supercompact cardinals, you can even use Levi collapses to make them into alphans and still have the tree property at aleph omega plus 1, as long as you pick the omega 1 in a very special way. So we prove that, and this is how we choose the lambda AB block. So for every omega sequence of supercompact cardinals above kappa, there is the right choice of omega 1, and by pigeonhole principle, we get 2 blocks, A and B, such that for both of them, the choice is the same. So, and then we use this theorem. So we have to choose omega 1. Let me call it aleph 1. So that it reflects every successor of a singular below kappa. Okay. And this took some work, but I wanted to mention it. So this is kind of the overview of the picture. And I don't know, if you give me 2 more minutes, I can talk a little bit about open problems. Or, or.
Yes, but shall we ask the audience?
Okay, maybe we can make it as part of a question.
Questions, remarks?
Okay.
Okay.
So what is the source of aleph omega squared being the first strong limit, where you're adding lots of sets in between in the prick reinforcing, right? Can you just
so the power set of kappa is blown up to what becomes so here below kappa, so kappa is singular strong limit, but there is all of these guys, they're not we have interleaved power set functions, and this is due to the this omega iteration of mutual forcings. So we do a lot of we add a lot of Cohen subsets to points below kappa, so that there is no singular strong limit below kappa.
So what happens to the aleph ends specific? I mean, what is the validity of the continuum in this model or whatever?
Well, the aleph ends, okay, so since there are omega many cardinals below kappa, we have, so all of the aleph ends are going to be, around the first prickly point. Okay. And, okay. So below kappa, between any 2 prickly points, we preserve omega many cardinals, right? This is the way for kappa to become aleph omega squared. So the first block is the Aleph-Ns. So if I go, and actually, so the Aleph-1 is chosen in this special way to reflect all successors of singulars below kappa. Well, Aleph-2 is also a former large cardinals. Like so Aleph-2 is also chosen in somehow a special way. It has to again do it has to do with this reflection, and while we're choosing it in this special, like, so we make Aleph-2, I guess people would call it generically Laver indestructible. So while adding many Cohen subsets, because 2 to the omega have to be Aleph-2. And then, so I guess the next Aleph-Ns that will be associated here with, so the prickly points themselves get collapsed, but the cardinals that are preserved are the cardinals corresponding to the A block and the B block. So the first block, the Aleph-Ns, will be the first reflection of the A block to the first prickly point.
So I was, can you explain, can you say something more about this preparation you mentioned? What do you do in this preparation?
Yeah, so in this preparation, I mean, there are several tasks. One is to prepare Aleph-2 in this generically Laver indestructible way. Then we want to prepare so that prepare L2. Also, we want to, so we start with kappa and many supercompact cardinals above it. We want to choose 2 of them so that they both reflect to, when you get the tree property at the successor of the singulars, you get the same tau, which is destined to become omega 1. And then we also prepare, so the main preparation is in the B block. So in the B block, we do like a Cummings, Foreman, Itai style omega many Mitchells in order to make the lambda BNs successors of each other with interleaved power set function and have the tree property hold. So we basically do Mitchell, well, omega Mitchells prep here. Well, and with 1 cardinal from the A block.
Okay, so if I understand correctly, from V to V prime, you
we do a lot of stuff.
Huh?
So, yeah, from V to V prime, that there is a lot happening. So
yeah.
Laver preparation for both of these, then making the lambda BN successors of each other, blowing up the power set of kappa, making sure that whatever is done here reflects below for measure 1 many sets of kappa. And then we need to consider 1 more auxiliary preparation forcing in order to make our prickly forcing like with a nice chain condition.
Yeah, and I guess it couldn't be done all at the same time with the unique forcing. It would be.
So I think the problem with all previous attempts was that people were only considering 1 block, and by people, including myself, of supercompacts above kappa. And one strategy was to do the preparation there and then force with prickly. The other strategy was to do the preparation within the prickly. And the problem was always how you stitch together the 2 prickly points below kappa. But doing these 2 blocks is what made it possible.
Thanks.
Okay.
But I do want to mention one like open problem that if people are interested in taking something here, well, let me, homework for the audience. Get the tree property at Aleph omega 1 plus 1 and the tree property at Aleph 2 at the same time. It looks simple when I write it down, but it's not, I don't know how to do it. This is and and yeah, and Aleph 2, yeah. And the reason this is hard is because of the reflection. To get it here, you have to choose L of 2, so it was a former successor of a singular, and you cannot do Mitchell there. But this is
Okay. Oh,
yeah, okay.
okay. Thank you.